In this lesson, we will learn how to describe conditions and applications for the electrolysis of molten salts and salt solutions. The electrolysis of a blue solution of copper sulfate is a very simple experiment to set up in a school or college lab. All that is needed is a solution of copper sulfate in a glass beaker. A source of DC electricity, such as a battery or DC power supply, is also required. Some conductive electrodes, usually graphite electrodes, are used. These are necessary to make an electrical contact with the solution. Finally, some wires are needed to connect the circuit together. A light bulb could be added to the circuit to indicate when current is flowing. The solution conducts electricity because it contains dissolved ions that behave as mobile charge carriers. When copper sulfate dissolves in water, two types of ion are released from this solid ionic compound. Positively charged copper ions, or cations, are present in the solution. Negatively charged sulfate anions are also present. From the water, there are a few hydrogen ions which are positively charged, and also a few hydroxide ions which are negatively charged. So there are in fact 4 types of ion present in the solution. The electrodes make an electrical contact with the solution because the graphite that they are made from conducts electricity. Graphite is a form of carbon that contains mobile electrons within its structure. Remember that graphite can also be used for high temperature electrolysis of molten ionic compounds due to its very high melting point. The electrolysis experiment described here is carried out on a solution at room temperature. The battery or power supply provides a direct current, also known as DC. In a direct current circuit, the current only flows in one direction around the entire circuit. The wires complete the connection to the battery to the circuit. We have built an electrolytic cell here, which is a circuit where electricity is used to drive a reaction forwards, one that would not otherwise occur spontaneously or all by itself. The electrolytic cell is used to carry out the electrolysis. Remember that electrolysis is the decomposition of a compound using direct current electricity. When the current is flowing, some changes will be observed after a short time in the glass beaker, and particularly at the electrodes. At the negative electrode, also known as the cathode, the greyish to black graphite will become a pink to orange colour as copper metal is deposited here. This electrode would in fact gain mass as copper atoms are coating the surface of the electrode. These copper atoms originated as copper ions in the copper sulfate solution. Copper is deposited at the negative electrode or cathode instead of hydrogen gas being formed, as it's less reactive than hydrogen. Remember that hydrogen ions were the other positive ions in the solution that could have arrived at the negative electrode to gain electrons and become hydrogen gas. At the positive electrode, or anode, bubbles of a gas will be seen. The gas is in fact oxygen, which originated from the hydroxide ions in the water. These products are formed as a direct result of the electrolysis process that is taking place. This process would carry on for as long as current is flowing and providing there are still ions remaining in the solution. If we make a small change to the experiment by changing the graphite electrodes for metallic copper electrodes, the results will be a little different. We will now have a copper cathode and a copper anode. The ions in the solution are the same as before, but some slightly different processes will be observed at each electrode. The main difference is that there will be no gas formed at the anode or positive electrode. The negative sulfate ions and hydroxide ions will be attracted to the positive electrode, but they will not change. They will remain in solution. Instead, metallic copper atoms from the anode will lose electrons and become positive copper cations in the solution. This process is known as oxidation. The oxidation process can be shown using the half equation Cu turns into Cu2 plus 2E-. The positively charged copper ions and hydrogen ions in the solution will be attracted to the negative electrode or cathode, which is also made from copper. Here, the copper ions only will gain electrons and become copper atoms. These copper ions are getting reduced at the cathode. This process can be represented by the half equation Cu2 plus 2E- makes Cu. Fresh copper atoms are therefore deposited at the copper cathode. If we checked the mass of the copper anode before and after the experiment, we would find that it has lost mass. This makes sense, as the copper ions created here have migrated through the solution to the copper cathode. The electrons left behind at the copper anode flow around the external circuit to the copper cathode. The copper cathode will have gained mass here as fresh copper atoms are deposited. The concentration of copper ions in the original copper sulfate solution will not change much at all. Since all we're doing here is effectively transferring copper atoms from the anode to the cathode, this experiment can be used as a way of purifying impure copper metal. Copper needs to be very pure for applications such as microelectronic circuits. This is because high purity copper is a very good conductor of electricity. If we take a lump of impure copper produced by smelting copper ore and make this the anode in this experiment, only the copper atoms from this piece of copper will enter the solution as copper ions. At the anode, the copper atoms in the impure copper leave their electrons behind and enter the solution as copper 2 plus ions. This process is oxidation. These copper ions from the impure copper will be attracted to the cathode, where they will gain 2 electrons and become copper atoms. They will become pure copper. At the cathode in this cell, reduction is taking place. Impurities in the impure copper anode will fall to the bottom of the electrolysis cell tank. This anode sludge, as it is known, can be further processed to recover other precious metals such as nickel and silver, which were present in trace amounts in the impure copper. So the impure copper anode will shrink or disappear. It is losing mass as copper ions are formed here and they enter the solution. The pure copper cathode will grow with fresh copper as the copper ions arrive here and become copper atoms. It will gain mass. The pure copper can be scraped off the cathode and used in high purity copper wiring and microelectronics. We have just seen that a copper cathode can become covered in fresh copper atoms in an electrolytic cell, provided that there's a source of copper ions and copper ions exist in the solution. It is possible to coat any metallic object that's placed at the cathode with fresh copper in this situation. In fact, if the solution contained ions from a different metal, they could instead be deposited onto the metallic cathode. This would only work if the anode were made from the same metal as the ions in the solution. This is the basis of electroplating, where a layer of metal is deposited onto a different metal surface that's the cathode in an electrolytic cell. It may be desirable to plate a layer of a more valuable metal onto a less valuable metal to make the object appear that it's made from the attractive precious metal. Silver or gold may be plated onto less precious metals for this purpose. This has even been carried out by fraudsters in the past to make a cheap piece of lead look like a piece of solid gold. Sometimes the metal plating is less reactive than the solid metal underneath, and the plated layer protects the bulk metal from oxidation or corrosion. This is certainly the case with silver or gold plating. Often, chromium or nickel are plated onto steel to prevent rusting and make it look more attractive. This is seen as chrome plating on vintage cars. The steel is protected as long as the chrome plating is not severely scratched through. As another example, if a brass fork were to be electroplated with silver, the fork would need to be placed at the cathode in the electrolytic cell. The electrolyte solution would need to contain dissolved silver ions from a soluble silver salt, such as silver nitrate. The anode would be made from pure silver. As DC electricity is passed through the cell, silver atoms at the anode would lose electrons and become silver ions in the solution. Oxidation is occurring at the silver anode. The silver ions would be attracted to the brass cathode, where they will gain electrons and become silver atoms. Reduction is taking place at this cathode. The silver atoms build up on the brass fork and it becomes electroplated with silver metal. The more current that passes through the circuit, the more silver will be deposited. It can take quite some time to get a reasonably thick layer with an attractive finish. Although the fork will not have the same density as pure solid silver, it will look like pure silver and the silver will protect the underlying metal from oxidation or corrosion. We will now look at a question to test your understanding of electroplating. A student electroplates a key with copper. What aqueous solution and electrode would be the best choices for this experiment? A. H2SO4 aqueous and a graphite electrode. B. H2SO4 aqueous and a platinum electrode. C. NaOH aqueous and a copper electrode. D. CuSO4 aqueous and a graphite electrode. E. CuSO4 aqueous and a copper electrode. Electroplating involves the use of an electrolytic cell to deposit a thin layer of metal onto another metal surface. An electrolytic cell needs a power supply. In this experiment, a simple cell is used to provide the direct current electricity. Our simple cell has a positive terminal and a negative terminal. The positive terminal is called the anode, and at the anode we would expect to find a source of the metal that is going to provide the plating. In this scenario, the metal that is providing the plating is copper. So in this experiment, the anode needs to be an electrode made from a piece of pure copper. At this electrode, copper 2+ ions will be produced. Copper atoms from the anode will leave 2 electrons behind on the anode and they will enter the solution as copper 2+ ions. The anode is therefore the site of oxidation here, and the electrons will flow from the anode to the cathode, which is the negative electrode. In order to plate the key, which is placed at the cathode in this circuit, with copper, we need copper ions to move through the solution and become copper atoms again at the cathode. Since we need a copper electrode to maintain the concentration of copper ions in the solution, we can reject any answers that suggest any other electrode should be used. Answers A, B and D are therefore not correct. Graphite is a form of carbon and it won't provide any copper ions at all. Platinum is a completely inert metal and it won't provide ions either. The aqueous solution in the electrolytic cell must contain dissolved copper ions. These copper 2+ ions will move to the cathode where they will gain 2 electrons and become copper atoms again, plating the key. This is the site of reduction. Since the solution must contain copper 2+ ions, we can reject answer C. In answer C, we see a solution of sodium hydroxide. Aqueous sodium hydroxide will contain aqueous sodium ions and aqueous hydroxide ions. These can be written as Na plus Aq and OH minus Aq. Aqueous sodium hydroxide will not yield any copper 2+ ions, so it's not the right answer here. Aqueous copper sulfate, or CuSO4Aq, does yield aqueous copper 2+ ions. Answer E is the correct answer, as we have the correct solution and the correct electrode. Let us now review the key points from this lesson. An electrolytic cell uses an external direct current power supply to drive a chemical reaction. Impure copper can be purified in an electrolytic cell by placing it at the anode in a solution of copper sulfate. Electroplating involves depositing a layer of a metal onto another metal surface using an electrolytic cell. The metal to be plated is placed at the cathode in the electrolytic cell. Electroplating is done to protect metals from corrosion or to improve their appearance.